So we're covering chapter 16.2 on the mathematics of waves. So unfortunately, there will be some math we have to deal with waves, right? The last section, we kind of cover like what's physically happening with the waves, right? How to describe these things called wavelengths and frequencies and the speed of the wave. Right now, we're gonna get into kind of like the minutia of how to write equations for waves, okay? So at the end of the class, we should be able to mathematically and graphically describe a wave and understand the properties of these waves. And that way, when we see a wave, we can actually say, oh, that's the wavelength of the wave. That's the frequency of the wave. And that's the way, and the reason that when you multiply the two together, you actually get the speed of the wave, okay? So let's look at this little kind of a still animation, right? So let's say I can even bring my little wave machine. What did I do with it? Okay. Right. Should have set this up before I start talking. Right. So wave machine, right? This is not as cool as the one I showed you guys on the video last time, right? But you can make a wave machine out of just a string where, on one end, let's say on this end, right? You just wiggle the thing up and down, you can create waves, right? So I can actually create waves that are higher frequency, right? Notice that higher frequency creates shorter wavelengths, right? Longer, slower frequency creates bigger waves, right? So if I wiggle faster, it makes the wave shorter, right? So you can already see this inverse properties between wavelengths and frequencies by just me wiggling around the waves, okay? So in this little picture here, right, it's trying to show you that, well, if you have a wave, right, what's going to happen is that the wave actually travels forward along your string, okay? As it travels forward, right, the wave machine keeps making new waves behind it, right? So what happened is that the wave just the wavelength stays the same, but then you're going to get multiple wavelengths of the wave as time progresses forward, okay? Okay, imagine this, string doesn't stop here, just go on to infinity, right? If you have a little machine like this, you can actually just make a wave that goes from 0 to infinity as much as you want, okay? If you have infinite time to wiggle the string around, okay? Okay. To describe this wave mathematically, okay, right? This is actually a sine wave, okay? The reason it's a sine wave is that the wave machine, right, it starts off with a displacement of 0, or y equal to 0. It has 0 height, right? So the wave machine actually started off at 0, right? Unlike a cosine function would start with an amplitude, the maximum amplitude of 1, right? Or 1 times the amplitude, okay? But we want to describe a wave as a sine wave because we want that wave to start at 0. We can shift these around later, but okay, we're going to see is that, well, if we describe this wave using a sine function, okay? A sine function has a period of 2 pi, so every 2 pi, it repeats itself, right? Okay. I can write this little equation down here, okay? Where, okay, so that wave above can be described using this little equation down here, right? Where y is basically how high the wave is, up or down, okay? Now, instead of just being a function of, well, position, it's also a position of time. So it has actually 2 variables in it, okay? Okay. And it's gonna have some amplitude A, just like the oscillation stuff, right? And then to figure out where the wavelength fits in is actually multiplied by the x component, x piece of your variable, okay, with this 2 pi over the wavelength in front of it, okay? This is going to look complicated at first, but we're going to simplify it in a second here, okay? And then the time dependency comes in, right, as the speed of the wave times the 2 pi over the wavelength also, okay? This looks kind of wonky right now, okay? And there's 2 pi's everywhere, and you have to keep track of these 2 pi's, right? But one thing we know is that, right, the speed of the wave is always going to be the wavelength times the frequency of that wave, right? This is the key equation we want to know whenever we're dealing with waves, okay? Right, the frequency of a wave, right, is just, well, of even just oscillation, right? It's just omega, which is the angular velocity, right? Velocity. But in this case, we're going to call it angular frequency instead, okay? Because it basically does the same thing. It tells you how frequent my arm is going up and down, right? As opposed to measuring it in number of cycles per second, it's measuring it in radians per second instead, okay? You can actually solve this and plug it in here, right? And therefore, right, the velocity actually turns out to be the wavelength times omega over 2 pi, okay? And notice that we have something like this. If we plug that back in here, right? Let's just do an equal sign here. There's still this complicated stuff in front, okay? 2 pi lambda, right? And if we have lambda on top, omega on top, 2 pi on the bottom, right? All of this is still multiplied by time, okay? The 2 pi cancel out, the lambda cancel out with each other, right? This makes it a little bit better because, right, if we set v times 2 pi divided by lambda to be omega, which is true from just our derivation, right? This whole term here, let me just cross out the entire second term, right? Instead of writing this in this complicated way, it's just omega t, okay? It makes it a lot easier to deal with, right? As opposed to like a bunch of 2 pi, some v's, and some lambdas, and some t's, right? It's just minus omega t, right? The minus sign stays, right? Because we're not playing around with the minus sign yet. Okay, what about this stuff in front then? Okay, this 2 pi over lambda, right? If we don't want to deal with 2 pi's, we can actually call this thing, this is called the wave number, okay? We're going to define yet another variable, unfortunately, okay? We're going to define this thing called wave number, which is going to make it equal to 2 pi over lambda, okay? Has this weird units, okay? Because lambda has units of meters, right? And the top here has no units or units of radians, okay? Right, so this wave number actually has units of 1 over meters, inverse meters, okay? If you do that, right, then you did this replacement in the back here, right, with omega t, right? You do the same thing here, replace this with k, or the wave, what's known as the wave number, right? This equation comes out a lot cleaner, okay? Okay. In fact, I'm going to rewrite it, the whole thing on the right, sine of k. And be careful here, this k is not the spring constant, right? It's known as a wave number, okay? This is known as the wave number, okay? Where k is defined by that, okay? Okay, so this is a lot easier to, look at, and, if you see it, then you'll say, oh, that's a wave, okay? Okay, so this is actually a wave that's traveling from left to right, okay? This is a wave traveling from left to right. Okay. If you want a wave that travels from right to left, it's the same thing, but the stuff in here, this minus sign turns into a plus sign, okay? This is a wave that's traveling from right to left, okay? In other words, this is a wave traveling this way, this is a wave traveling this way, okay? So you can have waves traveling left and right, right and left, whichever direction you want, okay? So in general, the book makes this complicated equation where, it just writes that, oh, the general way to describe a wave, the amplitude of a wave, the displacement of a wave is the amplitude times sine of kx, which is the first piece here, and then this upside down plus minus sign, right? So it's minus plus, okay, times omega t, which is what we have up here. And in general, there could be a phase shift, okay, where the wave doesn't start, where the wave machine didn't start off at y equal to 0. It could have started off at y equals to 1 or -1, right? That allows for that phase shift. And usually we don't try not to deal with that too much because it just makes complicated algebra, okay? Okay. The reason that this solution, this is known as the solution to a wave equation, works is because it obeys this thing called a wave equation. So the wave solution obeys the wave equation. Hopefully the wording makes sense, right? The wave equation is actually this complicated second order differential equation. If you never heard of it, don't worry about it. We're just gonna plug the solution in and then play around with it and see what happens, okay? So the wave equation on the left-hand side is taking the spatial derivative. It's taking derivative with respect to x, okay? So if you go up here, right, this is a function of x and t, right? So you can take a derivative with respect to x, or you can take a derivative with respect to t. Either one works, right? So what happens is that the left-hand side is the second derivative with respect to x. The right-hand side, just ignore the little 1 over v part for now, right? It's a second derivative with respect to t, okay? So you're taking derivative with all the variables, okay? This 1 over v squared, we're gonna see that, oh, this v is actually the speed of the wave, okay? And we're gonna see how that happens, okay? Okay, so if you plug the left-hand side in here, okay, you're basically taking a second derivative of sine of kx minus omega t plus some phase shift, okay? Every time you take a derivative, right, remember, you change the sine function into a cosine function, right? And then you pop out a factor that's in front of whatever variable you're taking derivative of. In this case, since we're taking derivative with respect to x, the a pops up, right? Sorry, the k pops out, right? Right. Okay. So that's the first derivative. Oops. I'm gonna write it as the derivative. Okay. Sine turns into a cosine, right? Everything else stays the same. Okay. Now, to take the second derivative, now instead of taking derivative of sine, it's derivative of cosine, right? Derivative of a cosine is actually negative sine, right? When you take the derivative the second time, another factor of k comes out, right? So the only difference is that you get a negative a, and the k squared comes from popping out these derivatives, okay? So you flip the sine function into a cosine, and then you flip it back into a sine, right? So that comes out to be pretty interesting, okay? Right? The right-hand side here, right? If we do the second derivative stuff again, instead of popping out k's, you pop out negative omega. Does that make sense? Everyone okay with that? Right? Because we're taking derivative with respect to time, and that's the factor in front of t, right? When we're taking derivative with respect to x, we pop out k's. When we take derivative with respect to t, we pop out negative omegas, okay? Okay, since we did it twice, the two negatives actually cancel each other out, but then you still have this sine flip to cosine, flip to negative sine situation still, right? Okay, so what ends up happening is that if you divide these two together, actually, the thing is the inverse of this, okay? What will happen is that if you take this ratio here, you actually get, right, the negative cancel out, the a's cancel out, the sine of kx minus omega t plus phi cancel out, right? The ratio of this is actually exactly equal to omega squared over k squared, okay? Right? And that's actually exactly equal to the speed of the wave square, okay? So this is just an important thing, okay? So the speed of the wave, right, is equal to, since it's a square, right, it could be a plus or minus omega over k, right? So if you square root both sides, you square root this side, you square root this side, that means v is either equal to plus, or it could be minus omega over k, right? Right? So is this true? So let's check, right? So what the heck is omega? Omega, right? What was omega? Omega is 2 pi times the frequency, right? That's omega, okay? Right? And then k was defined to be 2 pi over lambda, right? Okay? Right? So let's plug this back in here and this guy back in here, right? So v is actually equal to, let's just deal with the positive stuff for now, okay? Omega was 2 pi f, And then K is 2 pi over lambda, okay? And then the 2 pi's actually cancel out. And since lambda is in the denominator of the denominator, so that's actually in the numerator, right? So we actually find that, right? This V is the speed of the wave because, right, even though we did this substitutions with 2 pi's and stuff like that to get rid of all the complicated looking stuff in the equation, right? It actually does recover back to whatever our knowledge that the speed of the wave has to be the frequency times the wavelength, okay? And this is true for any waves, okay? Just nice. Any questions about this before I go into the example? And it's going to be related to what we're doing on the worksheet today, okay? So this little example from the book, right? We're going to look at an equation for a wave. So you're given some equation for a wave, right? So in general, the wave could be, you know, some amplitude times sine of kx minus omega t, right? And in this case, we're given this as the equation instead of the general k, general omega, general a, right? Okay. And the problem asks you to find the amplitude, the wavelength, the period, and the speed of the wave. Okay. So how are we going to find that? Okay. So, right, this A is representing the amplitude, right? So what on the right-hand side here would represent that A? Can you guys tell from just staring at this equation? Right, 0.2 meters, exactly. So the amplitude, 0.2, and there's your answer for that, okay? Wavelength, right, is lambda. Is there something on this equation that can tell us what lambda would be? Okay, something up here. What letter would it be? Anyone? K, the wave number, right? Exactly. We don't, the equation doesn't explicitly write what lambda is. It does write what K is, right? K is actually equal to 6.28, 1 over meter. So don't get confused by this -1. It's just indicating the unit is 1 over meters, okay? Okay, so K is 2 pi over lambda. Therefore, lambda, right, is just going to be 2 pi over K, right? And K happens to be 6.28, and that's basically approximately pi. So lambda actually turns out to be 1 meter. Okay, you guys see that? I got the number 1 from there. Okay. What about the period, the wave? Okay, what letter on the equation up top should I be using to try to figure out the period of the wave? Should I be using y, x, t, a, s, I, n, k, x minus omega, or t? It's a little bit more complicated because there's like a second two-step relationship. Okay, so in this equation, we already used this number. We use this number. What's left? Right, you use omega, right? So how is omega related to t? Okay, omega is 2 pi times the regular frequency. But how is the regular frequency related to period? Is actually inverse of each other, right? So we know what omega is, which is 1.57. Okay, so therefore we can actually solve this for t. T is actually equal to 2 pi divided by 1.57. 1.57 is basically pi over 2. Okay, so the pi actually cancel out. This is 1/4. Okay, and since it's a period, it would have units of seconds. Okay, 0.25 seconds. Okay, see that? Right. In order to get to the period, I have to go through the frequency, right? And the frequency is related to the angular frequency. Okay, it's like a two-step relationship. All right. What about speed? Which two variables do I need to calculate what speed is? The speed of the wave is always what? The easy equation, or you give me the harder one. What is the speed of the wave? In omega over k, okay? So that's the one with the fraction. That would work exactly, right? So you kind of already know what those are, okay? I'm gonna do this, and then I'm gonna do the lambda times f version also, okay? So omega, right, is just 1.57, right? And then k is 6.28, right? So this actually turns out to be 1/4, okay? And this will have units of meters per second. Okay. I'm gonna do the wavelength times frequency version, right? Because that to me is easier to remember versus omega over k. But hopefully we come up with the same answer, okay? The wavelength is 1.0, this is in meters, okay? The frequency, okay? I do this right? Omega over k. Oh yeah. That's right. Oh, okay. Yeah, you guys didn't catch my bad algebra, right? This period, let me erase that underscore, right? Remember, something that's a denominator and the denominator goes in the numerator, right? So this is the period is actually 4 seconds, not 1/4 of a second, right? Right. Made a bad algebra mistake. Sorry about that. Okay. And then the frequency is 1 over the period, and therefore that's the 0.25 seconds, right? So this is 0.25 seconds, 1 over seconds. Okay. And therefore actually 0.25 meters per second. Okay. Notice that whether I use omega over k or lambda times f, I get the same answer, right? Okay. So I want to show you guys is I'm going to graph this. Okay. And this is something that I think the book attempted to do, but I think this is an easier way to think about it, right? So I'm going to copy down the equation we're trying to graph. Y equals to 0.2 m meters times sine of 6.28. Okay. In fact, I'm going to write 2 pi here, right, times x. I'm going to ignore the units for now. Okay, minus, this is going to be pi over 2 times t, okay? Right? I'm going to do this. I'm going to graph the wave of y versus x for t equal to 0. Okay, what does that mean is that I'm going to, since there's 2 variables in here, I can only see how it turns out to be, I can only graph it versus one of the variables, right? What I'm going to do is I'm going to set this one variable to 0 and look at how the rest of the equation look like, okay? So in that case, what the equation will look like is y as x comma t equal to 0, right? 0.2 sine of 2 pi times x, but instead of writing t, I'm going to write 0 instead. So that's minus 0, so we can just ignore that part, right? Okay. It's a really bad comma there. Okay. So that's just a sine function as a y versus t, x. So on the horizontal, we have x, we have y on the vertical, okay? And the amplitude is 0.2, negative 0.2, okay? Since this is a sine function, it's gonna start off at 0, okay? Right? And the way I like to figure out how to graph sine function is I wanna know where the zeros are, okay? Okay, so, right, when x is equal to 0, sine of 0 gives you 0, right? But sine of pi is also 0, 2 pi is 0, 3 pi is 0, 4 pi is 0, 7 pi is 0, and so on like that, right? So I want to figure out when the sine function is going to get to some integer multiples of pi, right? The first time I'm going to see it is get actually x equals to 1/2, right? When x is equal to 1/2, I'm going to have sine of pi, right? So I'm going to start marking my x-axis, okay, with x equals to 1/2, or actually 0.5, since we're doing the graph, okay, and then 1.0. Let me space this out a little bit more. Sorry. 0.5, 1.0, 1.5, 2.0, 2.5. Because I know, right, 0.5 times 2 pi is going to be 1 pi, which I know sign is 0 there. 1 times that is also going to be 0. And 1.5 times pi is 3 pi. That's also 0. So I know where the wave is going to hit 0 all this time. So that way I can actually draw a wave. And I just want to make sure it hits 0 at all those points, okay? I'm going to draw a little wave like this. Right. So you see how I'm able to just draw this by hand and dropping my pen? Okay, makes sense? Okay, that's to me the easiest way to draw a sine wave. I mean, I misaligned it, but okay. I just find all the zeros, okay? And then I know that I have to go through all those zeros all the time, okay? Right? The other thing it asks you to do is actually plot y versus time instead, okay? That means we're gonna set x equal to 0, okay? This equation, right, it's gonna be y for x equal to 0 versus time. So that's the variable we're gonna be plotting against. It's still 0.2 as amplitude. Sine, okay, and supposed to 2 pi x, we get 2 pi times 0. So that whole term turns to be 0 minus pi over 2 times time, right? Right. So since there's a minus sign in here, and sine is a minus sign with a g, and sine without the g is an odd function, we know this is actually going to be an upside down sine wave. Okay. Okay. Right. So once again, I'm going to employ the same strategy, knowing that any multiples of pi's, I'm going to get zeros. Okay. And supposed to plotting versus x, we're going to plot versus time. Okay. The amplitude is still the same, 0.2, 0.2. Okay. Right. So I want to know when the sine function is 0. Well, it's 0 at 0. But right, when t gets to 2, that's when I get to 1 pi, right? So 2, 4, 6, 8, yeah. Shouldn't the top one be positive? Yes. Thanks for catching all these little mistakes. Okay. Being on your toes, so to speak. Okay. So instead of marking 0.5, 1, 1.5, and 2, I'm going to mark this 2.0 because that's when I know when the first 0 is going to come, right? Okay. 4.0, 6.0, 8.0. Okay. And now when I draw my sine graph, I just have to make sure my line goes through 0 at those points. Okay. Okay. That makes sense? And that's how you draw these two waves. So one is how the oscillation go up and down as a function of time. So it's just basically my arm going up and down. Okay. Let's do this physically, right? The blue one is representing at x equal to 0, how is my arm moving up and down? Okay. The red line is showing you as the wave progresses, how it actually depends on the position as it goes up. Okay. So that's the idea for these two graphs. Okay. And it's important to have both because you have a function that has two variables, right? So you have to make two graphs in order to indicate how they depend on both of those variables. Okay, question? Yes, everybody, good. You guys are much better at this than I am, right? Because of this negative argument, good catch, right? It's an upside down sine wave. And I draw a right side up sine wave, okay? Right. Cool. All right, so I think we can work on the worksheet today.